On March 13, 1989, a wave of charged particles from the sun struck Earth's magnetic field, collapsing the Hydro-Quebec power grid in 9 hours. Today, an event of that magnitude would incur trillions of dollars in economic damage, destroying satellite infrastructure and plunging continents into darkness. Despite the stakes, current operational systems provide maybe 20 to 30 minutes of warning before impact. A new system called Scan is attempting to push that horizon to a full 24 hours. It is an open-source, physics-informed machine learning engine developed in India, built specifically to close this prediction gap. Preventing civilization-scale blackouts means we can no longer rely on reactive observation. We have to construct deeply predictive mathematical models, strictly bound by astrophysical laws. You need continuous data from the right vantage point. This diagram maps the Earth-Sun Lagrange point 1.5 million kilometers upstream. A satellite placed here is gravitationally stable, maintaining an uninterrupted view of the sun, intercepting the solar wind before it reaches Earth. Scan fuses decades of labeled historical data from the American GOES satellite network with real-time telemetry from India's first dedicated solar observatory, Aditya L1. By actively embedding known solar physics into a multimodal neural architecture and placing strict mathematical bounds on its uncertainty, Scan achieves forecasting windows previously unavailable to space weather operators. Predicting solar flares is difficult because flare onset is stochastic. Even advanced magneto-hydrodynamic models hit prediction limits because the solar magnetic field topology is chaotic. The data also suffers from extreme temporal autocorrelation. Minute-by-minute observations of the sun look nearly identical, which causes naive machine learning algorithms to overfit to quiet periods. Compounding this is a severe class imbalance. Major flares happen only 1 to 5% of the time. A model that simply outputs no flare every single minute will achieve 95% accuracy, that it will fail to predict every critical event. Resolving these pathologies requires abandoning standard machine learning in favor of an architecture explicitly constrained by the laws of astrophysics. The first branch of this architecture processes soft and hard X-ray light curves ingested directly from Aditya L1's SOLEX and HEAL 1OS payloads. These light curves feed into a temporal convolutional network. This diagram illustrates the 6 layers of dilated convolutions, scaling dilations from 1 to 32, which gives the network a 250 time-step receptive field. This wide field is engineered specifically to capture the slow pre-flare coronal heating that often begins hours before an actual eruption. The system also embeds the Newport effect directly by computing the time derivative of soft X-rays and feeding it as a strict input feature. It then ingests continuous wavelet transform coefficients to isolate quasi-periodic pulsations, oscillations linked directly to high-energy particle acceleration events. Branch 1 does not ask the AI to discover physics. It mathematically forces the network to evaluate established astrophysical signatures. The physical origin of these eruptions lies in solar active regions. These magnetically complex sunspot groups act as the fundamental engines of solar flares. To track their evolution, the system continuously ingests 21 specific magnetic parameters from NASA's SHARP database for every active region on the solar disk. These parameters are processed by a bidirectional LSTM, configured with 128 hidden dimensions. A bi-LSTM is mathematically necessary here because the free magnetic energy inside a delta-class region requires days of temporal memory to accumulate and build tension. Branch 2 translates the slow, physical buildup of magnetic tension into a predictive mathematical sequence. The third branch handles the real-time trigger mechanism by pulling solar wind data directly from the MAG and SWIS sensors aboard Aditya L1. It captures critical features like field magnitude, plasma beta, and the Alfvén Mach number. This provides immediate operational utility. If the magnetic field suddenly tilts southward at L1, it acts as a direct upstream warning that a solar wind is about to couple with Earth's magnetosphere. These 14 real-time features are processed efficiently by a compact multi-layer perceptron, generating a 64-dimensional output vector. Branch 3 operates as the real-time contextual anchor, connecting the historical patterns tracked by the first 2 branches to the exact present state of the solar wind. The outputs from the TCN, BI-ILSTM, and MLP then converge into a central four-head cross-modal attention layer. This attention mechanism dynamically learns which modality, whether it's the X-ray flux or the magnetic topology, dictates the current solar state at any given moment. To effectively train this architecture, AddityScan uses golden window sampling. Rather than processing endless irrelevant quiet periods, it chunks the training data into 6-hour windows, strictly centered on confirmed M-class flares and above. It applies a dynamic focal loss function that heavily downweights easy negatives, forcing the model to scrutinize ambiguous pre-flare signals. The model is then subjected to an incremental training pipeline, updating sequentially month by month to adapt to the 11-year solar cycle without catastrophic forgetting. The combination of cross-modal attention and targeted sampling successfully subverts the massive class imbalance of the sun's behavior. A major flaw in many operational systems is that neural networks are often overconfident. Raw probability scores are functionally useless for high-stakes decision-making if you cannot measure their reliability. AddityScan solves this with a 3-layer uncertainty stack. This dashboard displays the first layer, measuring epistemic uncertainty via Monte Carlo dropout, mapping a tightly constrained interval across 24 hours. By running 50 forward passes, it captures the variance and strict limits of its training data. The second layer applies temperature scaling to calibrate the outputs. It softens the logits to align exactly with empirical frequencies, driving the expected calibration error below 3%. The final layer uses conformal prediction to generate a strict mathematical guarantee that 90% of actual outcomes will fall within the stated interval. This mathematically guaranteed coverage interval provides the rigorous statistical boundary necessary for space agency operators to authorize high-stakes protective maneuvers. This predictive capability extends directly into Earth's orbit via the Strategic Geo-Extension Module, designed to protect geostationary satellites from deep dielectric charging. By predicting the downstream relativistic electron flux environment, it safeguards crucial orbital infrastructure, including India's IRNSS and NAVIC navigation constellations. The performance metrics reflect this capability. In its final, fully fused Phase 2 model, AddityScan achieved a true skill statistic of over 0.8. For context, the current operational human forecaster baseline at NOAA sits at roughly 0.5. By releasing the entire codebase and weights as open source, AddityScan establishes a public infrastructure for space weather forecasting that any agency can deploy and verify. By encoding solar mechanics into a machine learning framework, the system converts Aditya L1 telemetry into a 24-hour forecast that consistently outperforms current human operational baselines.